by indicating a bit of a difference between what you think we're talking about and what I need you to recognize as how we deal with simple harmonic motion. You think, I believe, that we're talking about a box on a spring. And we spent a lot down that road. I really wanted to use this yesterday, and I'm going to use it today because all the people who have had AP Physics 1, they know what I'm about to do here. And you guys who have never had AP Physics 1 or didn't have it with me, there are stages of a simple harmonic oscillator. The way AP tends to test this is they sprinkle simple harmonic oscillations inside other problems. Have we seen problems that involve a mass on a spring before? In almost every circumstance of those, I've taken away the question that had to do with simple harmonic oscillations. But they ask them all the time. And they use things about simple harmonic oscillators to get other information out of the problem. So I'm going to talk to you about what you should know about all this. This represents half of an oscillation. The top part is the system at rest, but this represents half of an oscillation. For it to be a complete oscillation, it has to return back to where it started. This only does half of the motion. So what I think you should do at the start of this is mark where equilibrium is. This is the equilibrium position. We know that because the initial one at the top is the one that's our starting system. That's where our system is at rest. So this is where equilibrium is relative to the rest of the problem. So I'm going to start here at the very top. With the system at rest, this system is at equilibrium, and therefore the net force is equal to 0. We're starting at the beginning of the problem before we've actually added any energy to the system. So at this moment, net force is 0. It's important that you recognize that a few days ago, I had set this here. System's in equilibrium right now. When I add the weight, the equilibrium position changes because with this system, there's an external force, gravity, that acts on the system. This system is different than the sideways system, where equilibrium is and what we define as equilibrium changes. So we're defining the equilibrium position on purpose, and it's something that you have to do in any kind of simple harmonic oscillator and understand why the equilibrium position would be different on different kinds of oscillators. This represents the net force equals 0 position. That's why this is equilibrium. When I lift it up and drop it, it oscillates back and forth about that position, which is not the relaxed position of the spring. So you have to understand how your system compares to the ideal system. So our system is the ideal system, so equilibrium is the relaxed position of the spring. But equilibrium is still defined as the point where net force equals 0. That's important. It is defined where net force equals 0. And that's different for different systems. So we do work on the system by pulling out the mass. So this is us adding energy to our harmonic oscillator. All harmonic oscillators require an external input of energy to get them started. For us, this is the amount of potential energy that we have added to the system while doing work. This is the initial state of the system, so this also represents T equals 0, and currently V equals 0. But our position is at the amplitude. We're assuming that we're letting the system go at T equals 0, which means that at T equals 0, we are also experiencing the maximum force, We're at maximum amplitude, so that's maximum force. And since we're at the max amplitude, I don't need to say max amplitude. Amplitude is maximum. So at amplitude, we are experiencing the maximum force. Also at the amplitude, because we're experiencing the maximum force, we're also experiencing the maximum acceleration. So acceleration is max here. Both of them are pointing towards equilibrium. Now, we release the system, go to the next point. The next point here is t is something greater than 0. We're a little time away from the start. The system has been accelerating for a little bit, but the displacement is now less than the amplitude. This means that the force has been reduced and the acceleration has been reduced. There's less force and there's less acceleration. But our system has acquired velocity, which means that the energy now is a mix between potential energy and kinetic energy. I don't think in this class we finished that, did we? Subbing in for X and V. You should. I'm not going to use the time today, but you should. I don't want to make a big deal about it, but you will be able to prove that this equals 1/2 k x naught squared. And you need to prove that. So take a moment, make sure you make that happen. And it should only take you a few minutes. Now, this position is just an intermediate position. It's not particularly important. When I say intermediate, it is transitioning to what I want to say is a more important place in this object's motion. So I'm going to advance to here now. And in advancing to here, I need to extend my equilibrium line. At this moment, our next position, this represents 1/4 of the period because we are back at equilibrium, so we are halfway to the other side. This will be 1/4 of the oscillation. At this moment, x equals 0. This also means that there's no elastic potential energy. In addition to that, both force and acceleration are 0. We are at equilibrium. This object is experiencing no force for this instant and no acceleration for this instance. On the other hand, velocity is at a max. This is the fastest it will be traveling, which also means kinetic energy is at a max. Now it's brief because the moment we pass through, two important things change. Although the velocity is maximum and the velocity is in this direction, in our next step, the velocity is still in this direction, but now we have begun to depress the spring. So the force has suddenly changed direction. And the reason is because x is now negative. And that's going to make the acceleration and the force change direction. So although it's still moving because it has inertia, the force and acceleration are now acting to stop the object, not speed it up. Now, all of this vector information, now I don't have to go through everything here, but I will state this. 1/2 mv squared plus 1/2 kx squared is still equal to 1/2 k x naught squared. But we have a mix of the two energies because we have both velocity and displacement. The fact that the velocity is negative and the displacement is negative doesn't matter, they're squared. Energy is never negative. Until our next chapter, where it will be. And finally, we'll make it to this position. The amplitude again. It's the negative amplitude. But again, we make it to this side. And at this moment, velocity 0, force and acceleration are again maximum, but point in the opposite direction. This represents t equals 1/2 of the period. And again, at this moment, all of the energy is in the form of elastic potential energy. And the cycle repeats. This is the basic pattern for all oscillatory motion. We study it because even a partial oscillation has to obey these principles. So if you pull a block back against a spring and you launch that block, well, the moment the block was released, even if it didn't stay attached to the spring, for a portion of its motion, it was in oscillatory motion. I want you to understand, that would be pulling the block back, starting here. Let me start here by pulling the block back and release it. Say it wasn't attached to the spring. If it's going another direction, when the block makes it here, it will shoot off that way. A common question on the AP exam is to ask, how long did that take? And you can't use a motion equation for it because the acceleration was changing the whole time. So what do you use? You use the period of the oscillation. If you launch something with the spring, you don't have something that tells you how long it takes to get launched, but you do know what the period of the oscillation is, and it was a quarter of an oscillation. Most students don't think of it this way, but any partial motion against the spring can be treated like it's an oscillatory motion, even if it never completes one oscillation. So we'll see some examples of that. I would have this available. For a while, it's important that you understand where the energy is in this cycle. It's clearly always moving between two places, kinetic and potential. Real systems don't retain their energy forever. Real systems, they will slowly lose energy over time. But these ideal systems, we say, hold on to the energy. There's always an exchange between potential and kinetic. It's not always as obvious as this. This is why the spring mass oscillator is our ideal system. It's very easy to label, very easy to write it out on a piece of paper like this. So what I want to do now is I want to transition to something different. I want to show how any system can be analyzed to see if it's a harmonic system, and analyzed further to see if it's a simple harmonic system. I want to train you on how to do that, although its likeliness on the exam is probably low. Their number one oscillator on the exam is the simple there's the simple pendulum and the physical pendulum. Those are the most likely places where you will see simple harmonic motion on the exam. So we're going to look at the pendulum today. And I don't say the small angle approximation lightly. The pendulum isn't a simple harmonic oscillator. It's an approximation of a simple harmonic oscillator. If you want the best chance of these notes being helpful, draw your picture of your pendulum big enough that you can put a lot of data on it. So what I mean by that is I'm going to draw the pendulum like this. I'm just going to take up a lot of the board. And a pendulum, technically, is something that we can't actually make in the classroom. A true, simple pendulum is something that you wouldn't make with string and a weight at the end. For it to be a true, simple pendulum, it has to be a point mass. attached to an inflexible massless rod. Real pendulums, even a small mass on a string, don't really behave the way a simple pendulum does. Real strings, they bend, they stretch, so their length is not constant the whole time. So the stuff we do in lab, it's an approximation of an approximation. The simple pendulum already is an approximation, and it's really hard to construct an actual simple pendulum. You'll notice that clocks never hang their pendulum on a string. They usually have it on a thin piece of metal or a thin piece of plastic. And you'll see that going back and forth. You don't see them hang their pendulum on a string because strings flex and bend while the object is swinging. And that is a distortion of an oscillation. So we assume that this is an inflexible rod of length L, and we assume that the pendulum bob is a point mass of mass M and has no other moment of inertia except for the moment of inertia of a point mass. Now, just FYI, I teach the pendulum to you guys from the standpoint of linear motion. I mean, I talk about it moving through space in meters per second. The entire pendulum conversation can be done in terms of angular motion, if you like, and deal with moments of inertia, net torques, and the like. The ending result is the same. And what I'm likely to do is pick one class and do the angular conversation with them, and one class do the linear conversation with them. I've chosen fourth period to do the linear conversation. So I don't know whether I will change my mind when seventh period gets here or not, but I believe that doing the linear conversation has its benefits. And it has to do with this. We are attempting to see if the forces that act on our pendulum can be described by Hooke's law. Now, to do that, it's not obvious whether this will work out or not from looking at it. I mean, how many forces are acting on the pendulum? Should be able to name at least something. Yes, ma'am? There's the force of gravity. Anything else touching the pendulum? Yes, sir? Yeah? Tension, yeah. So we have two forces that are acting on the pendulum. If we ignore things like friction and air resistance, there's the weight acting downwards and tension acting along that rod that's holding the mass. So the force acting on a pendulum is the combination of two forces, not one. Now, we have a couple of other problems that we have to deal with if we want to try and do this. The first problem is we need some points of reference. Drawing this blue line to try and indicate equilibrium. I know that if I allow the pendulum to be straight up and down and just put it at the equilibrium position, the net force on the pendulum would be zero. Would you all agree with that? If the pendulum were, down here, tension would be up, weight would be down. They'd balance out, net force is zero if it's at rest. Even if it were swinging, when the pendulum makes it to the bottom, again, even if it's swinging, the pendulum does swing to, the pendulum does swing to this point. Even with a velocity, there'll be a tension upwards, which will be greater than the weight, because it's in circular motion. But there is no current force acting to push it back towards equilibrium because it's at equilibrium. The horizontal force is zero. So this blue line, which all of you just drew all that out, but I'm going to take that away. This blue line is going to act as equilibrium because it's a good solid equilibrium. Now, I think I'm going to label this theta and indicate that we are at a moment in time where the displacement of the object is some amount away from equilibrium. And I'm not talking about pulling it out and letting it go. This is a pendulum. This pendulum is somewhere in the middle of its motion. Does everybody understand what I mean by that? So I'm just picking a point in time. And for the time being, I'm going to assume that it's swinging maybe back towards equilibrium. But I don't have to state that. We're analyzing forces. We're trying to see if we can say Kx is equal to Ma. That's what we're trying to see. So let's start by looking at the forces acting on the pendulum. Can you agree that there's two? We already had this conversation. Let's go ahead and draw them in. There is mg downwards and tension along the rod that's holding the pendulum. Now, just like with the spring mass system, we want to do a net force analysis of our pendulum. Because although we're trying to see if that will work out to look like Hooke's law, we have to begin by looking at the forces acting on the pendulum. When I look at this, we have to choose a coordinate system. This is two-dimensional. So we have a choice about whether we choose our coordinate system to be like this. That's one option. Or if we choose our coordinate system to be like that. Now, let me ask you, between the blue coordinate system and the red coordinate system, which one points in the direction the object's actually going to travel? Blue or red? Okay, so we should probably use a coordinate system lined up in the direction it's going to travel, because that way it's lined up in the direction of the acceleration. Now, you guys, I want to be careful here. The object actually has two accelerations. There is a radial acceleration, which is along the direction of t, because it's in circular motion. And there's a tangential acceleration, which points back towards the blue line. You understand what I'm saying? I'm not ignoring one of them, but I'm only interested in the acceleration that is attempting to restore it to equilibrium. So that's the one I'm focused on. So I'm going to draw in my coordinate system a little more carefully than I had before, so that it's easier for me to see it and easier for you to kind of see it too. Now, we've done this problem before, and I'm not going to spend a lot of time explaining myself. This is also theta. So there is a component of the weight this way, mg cosine theta. And there is a component of the weight this way, which is mg sine theta. Now, just for argument's sake, this is the y direction, and this is the x direction. The net force in the y direction is not balanced, but that is causing circular motion. I don't need to worry about it. So I'm not going to worry about the net force in the y direction. I'm going to worry about the net force in the x direction, where there is one unbalanced force, mg sine theta. And that means I have mg sine theta equals MA. Now, can we all agree, because this one's harder, that if theta is a displacement in that direction, that the acceleration opposes it? You guys understand what I'm saying? Because the acceleration is clearly back towards equilibrium. I'm making that statement so that I can say that there must be a negative sign here that acts in the opposite direction of theta in order to indicate that the acceleration is back towards equilibrium. Okay, now here's the thing. I'm trying to see if this looks like this. And it clearly doesn't. For it to look like that, there has to be a constant times a displacement. And what I have is a constant times the sine of an angular displacement. So I don't have what I want. But there are other ways to write sine. For example, I don't know if you see it, but there's a big triangle here. You guys see that triangle? Well, this is the opposite side of that triangle. So sine of theta could equal the opposite side divided by L. Does that make sense? So I could modify my force equation and work in minus mg times the opposite side over L equals ma. Unfortunately for us, though, that's a problem. My object doesn't actually travel along that opposite line, does it? So saying that this is the displacement is wrong and isn't accurate. It would be close to it, perhaps, maybe, sometimes, but that's not really accurate. But there's a lot of reasons why I want to do that. Look, I get mg over L. These are all things that are constant about the pendulum. They have nothing to do with the angle. Times the opposite side, that's a displacement that could be measured in meters, and that equals ma. That would be convenient. Unfortunately, we know that the object actually travels along this arc length. I asked third period to tell me how long the arc length was, and they really couldn't. But can you tell me how long the arc length is? What's that? See, that's what everybody does, and they did that a lot in third period. That's a holdover of your math class, talking about the 360 and all that kind of garbage. I have an angle. It can be in whatever units I want, right? Because it's not stated to be in degrees, I don't have to make some fake conversion. I can just state it's in radians, and I can use something like delta x equals theta times r. That tells me what the angular displacement is and the angular length is. So we could say that S equals theta times L. That would be the arc length of that piece. Which would mean theta equals S over L. Bless you. Boy, if we could get S in there, that would be perfect. Because S actually represents a displacement. So the real question is, how is S equal to the opposite side length? Are these equal? If they were equal and equivalent, I could just swap out the opposite side for S. But by writing that, what I'm really writing is theta times L equal to sine theta times L? So if I distill that down, I'm actually asking, is theta equal to sine theta? So about half of you, maybe a third of you, know the answer to this. The rest of you don't. So who has heard of the small angle approximation? I said half and I get 3. Okay, so you guys haven't. Because you've not heard of the small angle approximation, it's not a cop-out. We know a pendulum swings with what looks like simple harmonic motion. However, it's not perfect. However, we don't need it to be perfect. We're going to use this as an approximation. We don't have much time, but we have a little bit. We're only going to do 4. Okay, got your calculators? How many radians is 1 degree? I want 4 decimal places. Somebody give it to me. It's not hard. Just 0.0175. The sine of 1 degree is 0.0175. All right, how many radians is 3 degrees? The sine of 3 degrees is 0.0523. How many radians is 5 degrees? The sine of 5 degrees is 0.0872. Big jump here. Gotta hustle. 0.3491. The sine of 20 degrees is 0.3420. So we're beginning to see that it breaks. Somewhere between 5 degrees and 20 degrees, it's not close anymore. But in the early small angles, very close. Would you agree? A lot of time in the last couple of days, starting from a basic premise of Hooke's law is what's providing our unbalanced force. And therefore, we said something like minus kx equals ma. And from here, developed a concept of a differential equation that led to a whole bunch of things, like x equals x naught cosine square root of k over m times t. And although I'm going to write all this out, don't write it down this moment, because you've already written it once. V equals minus x naught square root of k over m times the sine of the square root of k over m times t. And then acceleration equals minus x naught k over m times the cosine of the square root of k over m times t. And we even got more than this. It was suggested to you that we could replace, since we have to write it so often, k over m with the term omega. And the reason for that is omega has the appropriate units to be in radians per second. And we did a little bit of a unit analysis yesterday to show that that was true. So we could rewrite all of these with the omega symbol instead. So when I do that, we have omega times t in all of these, omega here, and omega squared there. Now, there's other implications too. The idea that V max is right here. So that's x naught times omega. That A max, which is right here, is x naught times omega squared. And more than that, we even talked about the fact that the period of the oscillation was 2 pi times the root of m over k, but in this shorthand, 2 pi over omega, which based on frequency being the inverse of period, this would be omega over 2 pi. Now, all of this is written out like this so that you can understand that if we find something in nature that has a similar structure, a constant times a displacement, then all we have to do is replace the constant here. Everything else stays the same. You see, there's simple harmonic oscillators everywhere, and all of them have a different restoring force. If we can figure out the restoring force, then we can apply all of this directly to them without having to reprove anything. All we have to do is figure out what the structure of the restoring force is. So part of the reason why I want this written this way is because this is almost everything regarding a simple harmonic oscillator except for energy. And it applies to all simple harmonic oscillators. Meaning this will be the structure of a pendulum, a physical pendulum, a torsion pendulum, and even other types of simple harmonic oscillators. All we have to do is figure out what the restoring force is. And is it a constant times a displacement? Now, I know that doesn't mean much to you right now, but in about 10 minutes, we're going to be looking at this from the standpoint of a simple pendulum, and you'll see exactly what I mean by that. But before we take a moment, plug these in and simplify. It's important that you do it. If you haven't tried it, you need to see what happens. I don't want to, is still contained here. At time equals 0, the velocity was 0. But immediately thereafter, the object started moving in the negative direction. It was explicitly stated in our equation for velocity that it would be in the opposite direction of the displacement. And therefore, our formula even bears that out. So although for that instant, x is still going to be positive, x remains positive for the first quarter of the motion, while the velocity is negative for the first quarter of the motion and remains negative until it finally stops. But at this point, just after a quarter of the period, the force and the acceleration are now changing direction.